Hello students, in this video we'll prove Liouville's theorem on geodesic curvature. So let's let R of U and V parameterize an isothermal surface along with W hat of t, a unit vector field. This is a vector field over a curve on the surface. So the curve on the surface looks like what? Looks like R of U of t, V of t, like so. Then we have the following result. Then dw dt is 1 over 2 root eg, then times g u v prime minus e v u prime, plus the change in the angle theta, plus d phi dt, where phi is the angle between RU and W hat. Okay? So this is a beautiful lemma that relates the algebraic value of the covariant derivative of a unit vector field to the angle between one of the basis vectors in the tangent space. Okay? So how do we prove this? Proof. Okay, so the proof goes as follows. So dw dt can be written as de1 hat dt plus d phi dt, where e1 hat is of course just ru over root e, and e2 is rv over root g. With that configuration of vectors, I can conclude, therefore, that n hat is really what? Is really e1 cross e2. Beautiful. Okay? Now, I just need to compute this thing over here. So what is this expression? So de1 hat dt is the inner product of e1 hat prime with n hat cross e1, like so. That's the value. That's the algebraic value of the covariant derivative. And of course, n hat cross e1 is going to be e2 because it's a triply orthogonal system. So this is just going to be what? It's going to be e1 hat u prime plus e1 hat v prime with what? With e2 hat. Okay. Now let's recall. So we can recall what? Let's recall. Well, if I do this e1 hat with respect to u, I'm going to have an RUU with an RV. So what is RUU? RUU dot RV. Well, that would be f sub u minus 1/2 what? E sub v. And then this one will be a what? This is going to give me a what? An RUV with an RV. So what's RUV dot RV? That's 1/2 G sub u. Okay? Now, it's an isothermal surface. So what can we conclude about FU? FU is equal to 0 because it's an isothermal surface, right? So now we're done, right? Because now if we look at these expressions over here, what does this become? Well, if I do the u derivative of this thing, by the quotient rule, I'll have an square root of e, partial derivative of the square root of e with respect to u, but then I'll have an ru dot what? Dot rv, and that's 0 because that's f, right? Similarly over here, if I do the derivative of g, if I do the derivative of e with respect to v, that'd be an ru dot rv 0. So all I need to do is look at the the numerator term, so I have an ruu dot what? Dot rv. RUU.RV is negative 1/2 EV. So this expression is what? Is negative 1/2 EV over what? The square root of E and G from the quotient rule. And then plus what? And then plus, and then those terms over there are hit with U prime. So these terms are over here of U prime. And then plus 1/2 GU V prime over the square root of E G. And that proves our little lemma over there. Beautiful. Okay? So now how does this relate to geodesic curvature? Well, now what I'm going to do is I'm going to let W hat be a derivative of a unit speed curve, right? So let's let, this is Liouville's theorem of many. And the good news is that starting tomorrow, we'll start filming some more lightboard videos. And the lightboard videos are going to transition to complex variables. And we're going to talk about Liouville a lot when we do complex variables, which is going to be very exciting. I've had a lot of requests for complex variables videos, so they're coming up lightboard style starting tomorrow. Great. All right. Tomorrow evening, probably. Okay. Good. So what's Liouville's theorem? It says let's let gamma be a unit speed curve. On this surface. And that just means the surface is isothermal, right? Then the geodesic curvature of this unit speed curve is going to be the geodesic curvature of the curves when the parameters v are constant times the cosine of phi plus the geodesic curvature of the curves u are constant times the sine of phi plus d phi ds. And that's Liouville's theorem, okay? Now we know how to compute these geodesic curvatures over here, right? So what are those geodesic curvatures going to be? Okay. So let's think for a second here. So good. So what's K? So proof. So K geodesic V are constant. Of course, if V is constant, that means what? When V is constant, then these terms are 0, so we're going to exactly have this up to the parameter speed. A negative what? A negative EV over, I would have ordinarily have a 2 root E root G, but then I have to hit that with U prime. And so U prime is with respect to T, so I have to do dt, du dt, and then dt ds, right? So I get a factor of dt ds, which is root E on that curve, right? So it's going to be a 2E root G. And then similarly, kg, when U is constant, is going to be what? Is going to be gu over what? Gu over 2g root E. Now if we fill in these relationships over here, take these relationships and fill them into the lemma, fill them in over there, and what will we conclude? We'll conclude from this that kappa g is going to be what? Kappa g is going to be this term over here, right? So that's going to be a what? Is going to be a kappa g b equals constant at what penalty? At the penalty of a root E times what? Root E times U prime plus kappa g. U is constant times root G b prime plus d phi ds. Beautiful. Okay. Now, what would, for example, so note, what is, so here's the note. The note now is that if I look at the inner product of gamma dot, that's a unit vector, with this unit vector over here, Ru over root E, what will that give me? Well, that's going to be a Ru U dot, so that's going to be an, that Ru is going to be an E, so E over root E is square root of E, so this is going to be a square root of E U prime. Good. But this is a unit vector, this is a unit vector, so that gives me the angle between what? That gives me the angle, of course here phi is the what? Phi is the angle between gamma dot, between Ru and gamma dot. That's what gives us the what? That's what gives us the geodesic curvature over here. Beautiful. Okay? But this is also equal to the cosine of theta. cosine of phi rather, right? So now our conclusion, of course, and then what will this have to be? By the fact that these things are orthogonal to each other, this term over here, root g v prime, is going to be sine phi, okay? So our conclusion, therefore, is that kappa g is kappa g v equals constant cosine of phi plus kappa g u is constant times the sine of phi plus d phi ds. And that is the proof of Liouville's theorem for the geodesic curvature of a unit speed curve relative to a unit vector field on a surface that is isothermal. Thank you very much.